Thank you very much. It's a very hard task for me to be the last presenter of the day, but I want to thank you all for staying for those last conferences. So thanks very much for this opportunity to present the point of view of a specialty thermoplastic player in regards to metal replacement in automotive. Today I'll try to be, let's say, simple, being the last, with simple questions. Why is metal used today in automotive? Why should we replace it with plastics? Where to focus on the car? Because we heard today that there is still a lot of potential for metal replacement. How should we replace it to be successful? And at the end, I will conclude with some words about Polyone and get your questions if you have any. If we take one step back and look at the top 10 reasons why metal is used in automotive for years, it's probably due to those key functionalities and key properties of the metal. Would it be stiffness, impact, heat resistance, a very good creep and fatigue behavior? Would it be the conductivity, thermal or electrical, etc.? So it's a very robust material and plenty of different reasons, not only mechanical, why metal has been used and still used in automotive today. Why should we think about replacing metal with plastics today? We've heard about different points today, so I will not go into details. I will just review that with you. First of all, system optimization, which means for us in automotive, lightweighting and more specifically, the optimum performance to weight ratio. For one application, we cannot afford anymore to go for over-engineering or to use a solution that has worked for years and we say is good enough. There is space for optimization. The second one, which has been also discussed today, is design freedom to get to more complex shape, differentiated look, and the integration of function. The third one is the production improvement, where we understand that there are a lot of opportunities to avoid secondary operations by using thermoplastics. And finally, we talked a lot about this today, and that is driving our industry and our innovations. These are the regulation changes, and for our industry, the CO2 emissions and the fuel efficiency. Metal replacement in automotive is nothing but new. We've seen plenty of very nice examples today. And what I want to say with that slide is that historically, the reasons to change from metal to plastics were on mechanical application or semi-structural application. Future applications where there is still a lot of opportunity to make that improvement are still in the semi-structural direction, for sure, so mechanical application, but also with all the electrical and electronic systems entering the vehicle, those systems bring with them new requirements for the materials. Like they need to work together, all those electronic systems. They need to be protected. It has been mentioned, flame retardancy, for example, or electrical conductivity to avoid electrostatic discharge, this kind of thing. And these are the new requirements of those systems in the cars that open new opportunities for metal replacement. You will argue that plastics are not always containing the same functionality compared to metal. And this is the challenge, and this is the way to come to the point. You need to functionalize the plastics, and the current technologies allow us to make those functionalization. If we think about stiffness and impact on a very large range of temperature and extreme temperature, there are some very specific technology that would help you to make that change from metal to plastic, and I will tell you a little bit more later on. If you look at thermal management, for example, where the key property is the thermal conductivity, plastics, standard plastics, are not thermally conductive. What if you would make those plastics thermally conductive? Would that open some opportunities to replace metals used for their thermal conductivity? Same for electrical conductivity and electromagnetic shielding. And these are the three examples I will discuss later on. This goes to be successful, you need also to take into account a second dimension, which is redesign. The most common failure is to say, I have a design which is working for metal, I will keep this exact same design for plastics. You have much more potential to adapt the design to get the most benefit of those thermoplastics. Let's go through the different examples. The first one is how to improve and make sure you get high level of strength with thermoplastics in very tough conditions and temperature. One of the key technology I want to briefly mention here is the long fiber technology. For those of you who are not familiar with that technology, it all starts with continuous bobbins of fibers that goes impregnated by resins and additive, and they are cut in pellets of 7 to 25 millimeters, for example. Then you injection mold this kind of material, and the fiber length in the part is between 2 and 4 millimeters, for example, which is 10 times bigger than short fiber technology. You will tell me, so what? What's the difference? In fact, it creates a 3D skeleton of fibers. And this is creating a very, very strong structure in the plastic parts. It brings a very high level of stiffness and also impact properties that are strictly equivalent to magnesium or aluminum, for example. It has a very, very strong creep and fatigue properties equivalent to the ones of metals, and they run at extreme temperature, low or high, and have a very isotropic type of approach. So this is one of the technology that allows you to think about replacing metal, because in the automotive, polypropylene long glass fiber is a technology that has proven that this move from metal to plastic is possible. But this technology of long fiber is not only to be used with polypropylene or with glass fiber. It can be used with higher temperature resistance and higher performance polymer, like the nylons, PPS, and even higher performance, and also with alternative fiber than glass, like basalt and carbon. We heard about these ones. And if you combine all those technologies, the fiber and the polymer, you can get to very high level of performance, which can help you reach the metal replacement next generation. This is not an exhaustive picture, but it is just to mention what are the typical applications where you can think about using this type of technology to lighten the car and avoid the use of metal. Second example of the presentation, heat management. Here, basically, you have two strategies. The first one is, I decide to resist to the heat. The second strategy, where I will discuss a little bit more in detail, is I decide to dissipate the heat. I don't want to resist it, I want to dissipate it, to evacuate it. I'm sorry for that, it's late, but I had to come back with the three principal phenomena in the heat transfer. You have the radiation between surfaces, which is, let's say, to be forgotten in our automotive world at those, let's say, generic temperature we are talking. The two key phenomena are the convection from a surface to a fluid in watt per square meter Kelvin. And here you have some examples of convection factors for gases, so air, for example, and liquids in free and forced convection. Here in this arena, we are in a free convection. The air is not moving. Behind me, there is a big fan, and this is forced convection, the air moving fast. The last phenomena in this heat transfer is the conduction. And the conduction is through a solid, and it is driven by the material conductivity in watt per meter Kelvin. Here you have some examples of material conductivity. Non-conductive plastics are at 0.2, aluminum is 90, stainless steel is 15, and thermally conductive plastics can go up to 20 or 25 watt per meter Kelvin. And at school, we all learned that when there is a heat dissipation issue, use aluminum, it will work. And that's very true. It works perfectly. But is that the optimum performance to weight material nowadays in those heat management applications? That's the question I want to ask. And I will propose you a simple example. Imagine a stadium, and that was a risky business here. I was thinking to myself, should I take a picture of a stadium in Istanbul? Oof, that will be tough. If I pick the wrong stadium, I will have problems. So I pick a neutral stadium here. And imagine that the fan in the stadium corresponds to the heat to be transferred, the joules. The number of exits represent the conduction level, and the public transportation represent the convection level. Imagine it's the end of the game between Galatasaray and Fenerbahce, and there are a lot of calories in the stadium that needs to be evacuated. If you use standard plastic with only one exit, so a very low conductivity level, then you will have a limited heat transfer because you have a conduction issue. If you take the opposite example, where you have a lot of exits, so typically aluminum, people will be able to go out from the stadium, but the convection will be limited because the number of bus, tramway is limited. So here as well, the heat transfer is not optimum. The optimum case is where you have a corresponding level of convection, number of buses and trams, and a corresponding level of exits, the conductivity of the material. That will be your optimum engineering for your application. And this is exactly what thermally conductive plastics are aimed for. In this case, aluminum would be over-engineered. This would not work. The optimum solution will be thermally conductive plastics. This is exactly what they can, on top of additional features like electrical insulation or electrical conductivity, working temperature that can be very, very large depending on the remaining quantity of heat in the application, and also additional features. For automotive, it is very helpful in electronic engine control units, mechatronics, power electronics. It is of a high help in high brightness LED lighting because LED are very sensitive to heat, and you need to have a very, very precise heat management. And most of the time, well, the headlamps are in the front of the car. This is the area where the weight reduction has a very high value. If you could replace aluminum by thermally conductive plastics, you will have a lot of benefits. It's also a very efficient hotspot reduction solution and can help you in handling fluids like AdBlue for the Euro 6 regulation, and also wiper. Again here, a general overview of the typical areas on the car where this type of technologies, heat management, you can think about thermally conductive plastics instead of metal with much lower densities and similar performance. I will finish the presentation with the last example, is how to manage the electrical conductivity and those electric and electromagnetic phenomena on the car, which can be extremely dangerous and critical to the increasing number of systems coming from the E&E industry, the hybridation from the start and stop up to the plug-in hybrid type of system, plus all the infotainment, the car-to-car communication system. You need to make sure that your electric and electronic system run safe and without any interference between each other. And what is driving that is the electrical conductivity of the material that you would use for your casing or for your application. It can go from antistatic, dissipative, up to conductive, and all this with much lower density than metals. You can do that by controlling the material science and the fillers you use to make that technology work. And this has a high interest in the engine control unit, mechatronics, to control the electrostatic discharge and protect the electronics. EMI shielding, to make sure that the system would work together well without interfering to each other. And the last one is on the anti-explosion protection when you on the fuel systems on the car in general. With that, I want to summarize and conclude that today the automotive regulation creates additional technical challenges with the weight reduction, the engine downsizing, the electrification of the car for sure. They have a significant impact on the material performance requirements, opening for us metal replacement opportunities. Because today, optimum performance to weight is a must, together for sure with an appropriate part engineering and part design. The answer to that is functionalization of the plastics and the customization of specialty thermoplastics are opening valid alternatives to metals in numerous automotive applications. Just to finish, for those of you not knowing Polyone, we are a global specialty thermoplastic player where automotive and transportation account for a very significant part of our business. And if you have some questions, some ideas for your metal replacement projects, you have the opportunity to visit us on Plaster Asia those next days, or our team in our plants in Istanbul will be more than happy to welcome you and discuss your projects. Thank you for your attention.